So this is Young's double slit experiment. In this experiment, we take a source S and we have a spherical wavelets emanating from this source, and what we do, we place a screen here in front of this at a large distance, so that on the screen we will have a plane wavefront. So this distance is large. Now we make a two pinholes. You see pinhole like this. So this is pinhole. So very small circular openings. So what happens, according to Huygens principle, when this wavefront reaches here, this point suppose I call it S1 and this point I call it S2, acts as a secondary sources. Again these wavelets emanate from these sources S1 and S2, and according to Huygens-Fresnel principle, these two waves interfere. Now if I place a screen here, then on the screen, suppose here at point P, the two waves reach here. So they may here interfere in a constructive manner or a destructive manner. So thus you will get here more light, no light, more light, no light. So this is what the schematic diagram of Young's double slit experiment. In laboratory, we generally place this source at the focus of a converging lens, thereby producing a plane wavefront. The slits S1 and S2 were used to be circular at the time of Young, but nowadays we are using rectangular slits, thereby these wavelets are not spherical but cylindrical wavelets. So nowadays we study the interference pattern of cylindrical wavelets. Let us see mathematically that how the maxima and minima will be distributed on this screen. Mathematically we will see, we won't draw this type of diagram now. So now let us see, this is my slit. From here rectangular wavefronts are going on to interfere. I will not draw the wavefronts, it will fill my whole board, and these are going to form a interference pattern on this screen. So this distance between S1 and S2 is very close, and this distance D is very large. So with close and large V means this D is very small compared to this capital D. So with this, within this approximation we are solving the problem. Now here suppose we have a point P and we are interested to know that when the two waves here reach at P, then what will be there? There will be a maxima or a minima, or how they will interfere. So suppose these are the two S1 and S2 P are the two waves, one reaching like this, another one going like this. So two waves are there. Now whether let this position be y from measured from this axis, and whether the two waves will interfere in a constructive manner or destructive manner will depend on the path difference between them. Initially they are in phase, they are created from the same source, so they are coherent sources. So let us draw a perpendicular from here, and let us assume that the angular position of P is theta. So this becomes path difference. This is D. Now this angle is theta. So this is 90 minus theta. We can assume this angle then becomes theta. So this path difference between these two waves can be approximated as d sin theta. So the path difference between two waves arriving at P, we will call this as delta x, path difference. We will reserve the letter delta x for path difference, and this will be S2P minus S1P, S2P minus S1P. So delta x becomes d sin theta. Now when this theta is, when d is very large, S1 S2 is very small compared to this, and y is also comparable to this. So this tan theta is very small, so we can write sin theta and tan theta as same, and we can further write delta x as d tan theta, which can be further written as y by capital D, y by d. That is the relation between path difference, and this is y d by d. This is a very important relation. In problem solving, often we will be using that. If I move y distance from this axis, then what is the path difference created between the two waves coming from S21 S1? This is the path difference. Now depending on the value of delta x, we can tell whether there will be maximum light here, maxima will exist or minima will exist. So now if, let us see, for what values of y, what are the locations of P where we will get maxima. So we call the places where maximum light falls, where there is more brightness, that places are called bright fringes, and the distance between two consecutive bright fringes will be called bright fringe width. So the positions of maxima are called bright fringes, and the distance between two consecutive bright fringes is called bright fringe width. We will denote this as beta brightness. Beta is the distance between the two consecutive brightnesses, and so beta brightness. For darkness we will use beta darkness. So now let us locate where will be the maximas. So we will see where this delta x will be equal to n lambda. Now you see, delta x is equal to n lambda for brightness, correct, for brightness delta x is equal to n lambda. That means n lambda is equal to y d by capital D. Already we have seen that delta x is y d by d. So for brightness we require this. Now there are different positions of y for which we have different values of n. Here n is equal to, 0, 1, 2, 3 dot dot up to infinity, integral values, positive integers values. So we said we will call yn, means nhy is equal to n lambda d by d. Now already we have seen here that the distance between two consecutive brightness will be called bright fringe width. So beta brightness will be written as yn plus 1 minus yn. Yn plus 1 means n plus 1 lambda d by d minus yn means n lambda d by d. So here n cancels, so it becomes lambda d by d. So beta brightness is equal to lambda d by d. The consecutive brightness are separated by lambda d by d. I will write it here. Beta brightness as lambda d by d. Now let us see what are the locations of minima. Minima means darkness. Light plus light, more light, that is brightness, or light plus light is no light, that is darkness. So let us see where we can have a minima. Now let us see what are the locations of the minima. So when minima will be there, so at minima we have path difference delta x is equal to 2n plus 1 lambda by 2, where n is equal to again 0, 1, 2, 3, 4. This is, now what is delta x? Already we have seen that it is y d by d, y small d by d, that is equal to 2n plus 1 lambda by 2. Now since there is not a single y, there are many possible p's, many possible y's for which this will be there. So better call it yn is equal to 2n plus 1 lambda d by 2d. Again the same, when there is a minima at p, we will call it dark fringe. The distance between two consecutive dark fringe will be called dark fringe width. So we will call beta darkness, that is the dark fringe width, as yn plus 1 minus yn. What is yn plus 1? It will be n plus 1 means 2n plus 3 lambda d by 2d. And what is yn? The same thing, 2n plus 1 lambda d by 2d. What we got? This 2n cancels. This is 3 minus 1, 2, 2 cancels. Lambda d by d. Thus we arrived at a result where beta darkness and beta brightness have the same values. Means brightness, between two brightness, whatever distance is there, between two darkness, same distance. That means the fringes are uniformly distributed. So entire screen will have a uniform fringes there, and the center, at the center the two waves interfere with a 0 paths difference, and we call this point as central maxima. Now next let us see the intensity distribution on the screen. Now let us see the intensity distribution on a screen in a YDAC. At this point, we call this point as central maxima. Central maxima, the path difference is 0. Now let us see that if I move at a distance of y, then the path difference, suppose this is the angular position of theta. So at this location y, or what will be the intensity, or how the entire screen is illuminated, how the intensity of light is distributed over entire screen. So in order to calculate, we see intensity is proportional to amplitude square. So now if we have here a wave called from S1, we have E1 is equal to A1 sine omega t plus theta 1, and from S2 suppose we have E2 is equal to A2 sine omega t plus theta 2. Then when these two waves will add up at P, the resultant intensity, suppose I write amplitude, is given by A1 square plus A2 square plus 2A1 A2 cos theta 1 minus theta 2. Since intensity is proportional to this, so suppose that proportionality constant is K, so we can write Ka square K A1 square plus K A2 square plus 2K A1 A2 cos theta 1 minus theta 2. So we will get intensity. Now suppose this is I1 intensity, it is I2 intensity, it will become 2 root I1 root I2 cos theta 1 minus theta 2. That is the phase difference between them. Let us call this phase difference as phi, cos phi. Phi is the phase difference where phi is equal to theta 1 minus theta 2. This is how intensity will be distributed. Now, at the maximas, we have constructive interference. So, there cos phi value will be 1. So, cos phi will be equal to 1. So, I max will be equal to I1 plus I2 plus 2 root I1 root I2. This is the expression for maximum. Now, if generally the slits are symmetric, identical, so they allow identical intense lights. So, we can write if I1 is equal to I2 is equal to I0. Suppose here intensity is I0, then we will have I max equal to I0 plus 2 root I0, that is I0 plus I0, 2 I0, this is again 2 I0, so 4 I0. So here at maximas you will get 4 times intense light. What about minima? So when this value will be 1, when this value will be minus 1, then this will be negative term. So I minima will be I1 plus I2 minus 2 root I1 I2. If I1 is equal to I2 is equal to I0, I min is equal to 0. That means the minimas will be complete minima if these two will be same. It will be complete darkness. But if they are different, then their darkness will not be complete darkness, there will be some less intense light there. So, the contrast of the fringe edge will be here poor. So, if intensities of S1 and S2 is correct, means they are same, correct means same, if they are same, then maximas will be 4 in I0, minimas will be complete 0, and there will be good contrast of fringe edge. If they are different, then the contrast of fringe edge will be poor. So, if I1 is equal to I2 is equal to I0, then I is equal to this, and where phi is the phase difference between the two waves, we can write this as 2 I0 plus 2 I0 cos phi. I will be 2 I0 common, 1 plus cos phi. This will be this, again it will be I is equal to, I can take 2 outside, it will be 4 I0, 1 plus cos phi will be again cos square phi by 2, where phi is the phase difference between the two waves from S1 and S2. So, this will be how intensity will vary with the phase difference. Now, you can see here phase difference phi, if I want to relate with y, the phase difference phi is actually given by 2 pi by lambda into delta x. So, if the path difference between S1P and S2P is delta x, we can relate phi as this. Further, also we know that delta x, if I move y distance, the path difference will be equal to y d by d. So, if once I know what is y, at that location we can calculate delta x, so phi, so will be I. So, if I put all the thing everywhere, we will get phi is equal to 2 pi by lambda delta x y d by capital D, and this phi, if we will put here, that intensity as a function of y we will get. Now, let us draw a diagram to show how intensity varies with this. So, now let us see how the intensity of light is distributed on the screen. So, the expression we got is 4 I naught cos square phi by 2. This is the expression of intensity. Here I naught is the intensity of light here, and I naught is the intensity of light here. Now, you see here, this is the screen where we have to study the interference pattern. Here this is central maxima. We call this point as central maxima. So, here this intensity of light is 4 I naught. This is 4 I naught. This is a special graph. So, when the intensity of light is less, you see this becomes 0. So, this is my first darkness. So, here I will get no light. If these two are same, no light. Here 4 I naught, 3 I naught, 2 I naught, it decreases like this. Again here at this location it becomes 4 I naught. So, all the brightness, this again 4 I naught, 4 I naught. Then this is again 4 I naught, and then this is again 4 I naught. So, all the brightness are equally bright. Their intensities is 4 I naught. Here we will give a nomenclature of beta 1, beta 2, first brightness B1, B2, darkness D2, D3 dot dot. So, there will be many brightness and darkness spread on the upper half and on the lower half. This will be called first darkness, first brightness. Central maxima is this one. We won't call it first brightness. First brightness means next after central. Then D2 like this. So, this is how the intensity will be distributed on the screen. Now, let us take a problem in which we will calculate, this is 4 I naught, and when it is 2 I naught this way and this 2 I naught. So, let us calculate this width. Let us calculate the width which separates 2 I naught intense points. So, the 2 points whose intensities are separated has a intensity 2 I naught, and let us see at what distance they are separated.